Welcome to a screencast that will go through the calculations involved in a weak acid, strong base titration. And the example we're going to use is involving lactic acid, that's our weak acid, and sodium hydroxide, that's our strong base. So we'll have a flask of lactic acid, our weak acid. We'll have a burette of our strong base, sodium hydroxide. We'll add the strong base into the weak acid, and we're going to calculate the pH initially, partway to the equivalence point, at the equivalence point, and after the equivalence point. And just as a note, what we'd expect for our results, we've seen titration curves before, and if we have a weak acid, the initial pH is going to be low, maybe not as low as if it was a strong acid, but pretty low initial pH. As we add strong base, the pH gradually increases as weak acid is reacting with the strong base. Conjugate base of the weak acid is being produced. Eventually, we get near the equivalence point where the pH goes up rapidly. At the equivalence point, we'd expect the pH to be higher than 7 because we have a strong base reacting with a weak acid. And then as we go past the equivalence point, initially the pH continues to rise very rapidly, but not too much past the equivalence point. The pH then starts leveling off somewhat at a fairly high pH because we're using a strong base, and the pH now will be not constant, but it's going up very slowly after the equivalence point. Okay, so first calculation, what's the initial pH? And note, we haven't added any base yet, so what we have is a solution of the weak acid, lactic acid. We're going to represent lactic acid by H-lac, so we don't have to write HC3H5O3 all the time. And then, of course, we have water as well, and lactic acid and water are in equilibrium with each other, forming small amounts of hydronium ion and lactate ion. And if we do the things we've done a bunch of times before, our initial, which is our nominal concentration of lactic acid, pretending it hasn't dissociated yet, and then our change, allowing it to dissociate, and our equilibrium. And then, of course, if we can look up a K sub A value for lactic acid, which we can, and it turns out that's 1.4 times 10 to the minus 4th, we can set up the K sub A expression in terms of the hydronium ion concentration, the lactate ion concentration, and the lactic acid concentrations. And we can solve this equation, substitute in terms of x, solve this equation, and we get x equals the hydronium ion concentration, which is 5.2 times 10 to the minus 3rd molar in this particular case. And what we would like is the pH, so we take the negative log of 5.2 times 10 to the minus 3rd, and we get a pH of 2.28. And that seems like a reasonable initial pH for a solution of weak acid. Now, the next thing we're going to do is calculate the pH after we have added some sodium hydroxide. And a thing to note about these kind of calculations, in our normal equilibrium calculations we've done up until now, we have concentrations of substances, we know our K value, hopefully, we set up our ice table, and then we calculate using the equilibrium constant expression, and we use molarities of substances. But here we actually have a reaction that's taking place, and then there's actually an equilibrium that is established after the reaction has taken place. And so we have to do two steps. We have to track the reaction first, then the equilibrium. And in order to track or follow chemical reactions and how much substances react and how much is formed, we have to use moles. So we have 25 milliliters or 0.0250 liters of the lactic acid, which is 0.200 moles per liter. So we have 5.00 times 10 to the minus 3rd moles of lactic acid. Now, we can write this a little more simply by noting that 10 to the minus 3 is a milli whatever, and so this is 5 millimoles of lactic acid. Now, similarly, for the sodium hydroxide, we have 15 milliliters, which is 0.0150 liters, times 0.150 moles per liter, the solution concentration, gives us 2.25 times 10 to the minus third moles of NaOH, or, in our shorthand notation, 2.25 millimoles of NaOH. Now, these are our starting amounts of these substances, and the other thing to note is when they are added together, the solutions are mixed, we also have a volume increase. So we had 25 milliliters of the acid solution, we've added 15 milliliters of the base solution, so roughly we have 40 milliliters of solution that has now been formed by these two substances, these two solutions combining. So what's going to happen if we have 5 millimoles of lactic acid and we add to that 2.25 millimoles of NaOH? Well, here's a little kind of cartoon schematic. Here's our LAC, here's our NaOH, and when the NaOH is dropped into the lactic acid, hydroxide can grab a hydrogen. So here's a hydroxide grabbing a hydrogen from the one lactic acid. Here's another hydroxide grabbing a hydrogen from another lactic acid. That forms water, which then just sort of disappears into the solution. And so what has ended up happening is some of our lactic acid still remains, but we have created some conjugate base lactate ion. And once the reaction has taken place, then we have lactic acid and lactate in equilibrium with each other and no more hydroxide left. So here's the reaction that takes place. Notice it's a one-way arrow because this is a weak acid reacting with a strong base. Very, very product favored. And we can still do our ice table, but note these are not equilibrium amounts necessarily. These are starting amounts. 5 millimoles of lactic acid, 2.25 millimoles of hydroxide from the sodium hydroxide. And what we'll do is we'll pretend they haven't reacted yet. So no lactate has been formed, and then water, of course, doesn't show up in the equilibrium or in our calculations. Now the change, the hydroxide will all be used up, so that will decrease by 2.25 millimoles. It'll be gone. That means that the lactic acid also decreases by 2.25 millimoles, and the lactate increases by 2.25 millimoles. So our quote-unquote equilibrium, which is really just the end result of this reaction taking place, is we have 2.75 millimoles of lactic acid left, hydroxide's been wiped out, and we've formed 2.25 millimoles of the lactate ion. So note, we've got some conjugate base formed, some weak acid left, and it is in 40 milliliters of solution. So for our next step, when we're going to have to do equilibrium calculations, we want to determine the molarity because that's what we need in equilibrium calculations. So we take our 2.75 millimoles of lactic acid that's left, divide by 40 milliliters of solution that's been formed. Notice that millimoles divided by milliliters is the same as moles divided by liters. So we have 0.0688 molar lactic acid. And then same idea, but different numbers for the lactate. 2.25 millimoles divided by 40 milliliters gives us 0.0563 molar lactate ion. So we have lactic acid and lactate ion in equilibrium with each other. Now, after we've tracked through what takes place during the reaction, we have lactic acid and lactate ion in equilibrium, and we have to deal with that equilibrium aspect and do that in our calculations next. Now, if lactic acid and lactate ion are in equilibrium, we've dealt with this before. Here's the equilibrium equation. Notice we don't worry about NaOH anymore. That's all reacted. It's formed some lactate. There's some lactic acid left. We're still in the acid world, so this is the lactic acid lactate ion equilibrium. And it's our kind of standard ice table stuff, except our quote-unquote initial concentration is the ending concentration, or are the ending concentrations from the reaction step that we did previously. So we have 0.0688 molar lactic acid, we have 0.0563 molar lactate ion, and we're pretending that the reaction took place, formed these concentrations of lactic acid and lactate ion, and the equilibrium adjustment hasn't occurred yet. Now, in reality, the reaction takes place, the equilibrium adjustment is occurring all at the same time, but we can't really track that mathematically unless we separate it into two kind of artificial steps. So we've done the reaction step. Here's now the equilibrium part, and the H3O plus and lactate ion concentrations will go up because we're pretending there was no hydronium ion at the end of the reaction. The lactic acid concentration will go down. At equilibrium, we have the concentrations shown, and this should look just like what we've done before for acid equilibria, except we're not starting with 0 for lactate. Now, K sub A, of course, is 1.4 times 10 to the minus 4th, because we're still dealing with lactic acid. We set up our equilibrium constant expression, but this time it's not x squared over concentration minus x. It's x times 0.0563 plus x over 0.0688 minus x. And when we solve for x, which is H3O plus concentration, we get 1.7 times 10 to the minus 4th molar. And if we take the negative log of that to get pH, we get 3.77. Now, still acidic, somewhat higher than the pH we started with, but we haven't yet reached the equivalence point. In fact, we're quite a ways away from the equivalence point, and the pH is going up gradually. Seems quite reasonable. Okay, now the next step is what's the pH at the equivalence point. And we're going to use kind of the similar process to before, 2 steps, reaction, then equilibrium. And we have to deal with moles, and we have to remember that equivalence point means moles of acid that we started with and moles of base that we've added to the solution are equal. And so if we started with 5 millimoles of lactic acid, of course that means we had to have added 5 millimoles of sodium hydroxide. Now, to calculate what volume this is of sodium hydroxide, we take our 5 millimoles of sodium hydroxide, use its concentration of 0.150 millimoles per milliliter, and calculate that we need 33.3 milliliters of this sodium hydroxide solution to provide 5 millimoles of sodium hydroxide, which reaches equilibrium. And then, of course, we're going to have now a total solution volume of the 25 milliliters we started with and 33.3 milliliters of NaOH we've added to reach the equivalence point, so 58.3 milliliters total. Now, here's what we can sort of visualize is happening. We have our NaOH, or our hydroxide, that's being added to our lactic acid. The hydroxides go in, grab a hydrogen ion off of a lactic acid, form water, removing the hydrogen ion. The water goes into the solution, and all of the lactic acid has been converted into lactate ion. Now, the reaction between lactic acid and hydroxide makes lactate and water. So we've done this before, and now we'll track again. 5 millimoles of lactic acid has 5 millimoles of hydroxide added. We initially pretend the reaction hasn't taken place, so there's no lactate ion. And again, water we don't care about. The change, all of the lactic acid reacts, all of the hydroxide reacts. 5 millimoles of lactate are formed, or there's an increase in lactate by 5 millimoles. And at equilibrium, all the lactic acid is wiped out, all the hydroxide is wiped out, and 5 millimoles of lactate are formed. But now note, this is in 58.3 milliliters of solution, which gives us a concentration of lactate of 0.0858 molar lactate ion. Now note, we don't have lactic acid left, we don't have hydroxide left, we only have lactate ion, and lactate ion is the conjugate base of the weak acid, lactic acid, so we expect this solution to be basic. And we now deal with the equilibrium of this basic solution. And of course, what lactate ion does in an aqueous solution is dissociates the water slightly, makes lactic acid and hydroxide ion. And if we do our equilibrium ice table now for equilibrium stuff, our initial concentration of lactate is 0.0858 molar. Lactic acid and hydroxide are 0, hasn't dissociated yet, or at least that's what we pretend. Changes of -x and +x respectively, as we've seen before, gives us our equilibrium concentrations in terms of x. And now note, we have a basic solution, hydrolysis of water due to the lactate ion, and that's a K sub B expression. And we typically won't look up a K sub B for the lactate ion, but we can get the K sub B for lactate by noting that it's 1.0 times 10 to the minus 14th divided by the K sub A for lactic acid, which is 1.4 times 10 to the minus 4th. So K sub B for a base is equal to 1 times 10 to the minus 14th over K sub A for the conjugate acid. That's equal to lactic acid times hydroxide over lactate ion concentrations, which of course is going to be x squared over 0.0858 minus x in this case. And when we solve for x, we get 2.5 times 10 to the minus 6 molar, and we note that x represents the hydroxide concentration. So, since we want pH, we're going to take the negative log of hydroxide concentration, and then that will give us pOH, and then 14 minus pOH gives us pH, and that works out to be 8.40. And that seems about right. We'd expect our equivalence point pH to be higher than 7 because the acid's weak and the base is strong. Now, the last part of this problem is continuing past the equivalence point. So 15 milliliters of the NaOH beyond the equivalence point. So that means we have 33.3 milliliters to reach the equivalence point, plus 15 more gives us 48.3 milliliters total, times the concentration of the sodium hydroxide solution gives us 7.25 millimoles of sodium hydroxide that has been added. So here is our sort of visualization of what occurs. We've got lactic acid to which we add hydroxide. When the hydroxide is added, it removes hydrogen from the lactic acid, forming lactate ion. More hydroxide's added, more hydrogen removed, more lactate ion formed, and this continues converting lactic acid into lactate ion until all of the lactic acid has been converted into lactate ion. And then we still have a little more hydroxide to go. So if we keep adding hydroxide, we build up some hydrogen ion concentration in the solution, in addition to the lactate ion concentration in the solution we are already formed by getting to the equivalence point. Now, if we track this as we've done before through the reaction that takes place and the amounts of substances that react, initially we have 5 millimoles of lactic acid. We add to it 7.25 millimoles of hydroxide. We pretend the reaction hasn't started yet, so no lactate to begin with. The hydroxide and lactic acid amounts go down by 5 millimoles, so the reaction takes place until one substance is used up. In this case, it's lactic acid. That adds 5 millimoles of lactate ion that's being produced. And so at the quote-unquote equilibrium, which is really just the end of this reaction, if we're isolating the reaction that takes place between lactic acid and the strong base, hydroxide, we're left with 0.225 moles of hydroxide, no lactic acid, and we've formed 5 millimoles of lactate ion. And then, of course, these are in 73.3 milliliters of solution, which gives us, at the end of the reaction phase, we have 0.0307 molar hydroxide ion and 0.0682 molar lactate ion concentration. Now we have lactate ion in equilibrium with hydroxide ion, so it's a basic solution. We use the base equilibrium expression. Our initial concentrations are the concentrations we found by the end of the reaction. And again, we're assuming that we're going to separate the reaction from the equilibrium, and we'll start the equilibrium part with no lactic acid, no H-lac being formed yet. Now, of course, a little bit does form as the lactate ion hydrolyzes the water, makes a little bit of lactic acid, adds a little more hydroxide. And at equilibrium, we have the amounts shown, or the concentration shown in terms of X. We're still dealing with a base equilibrium, so we still use K sub B. That's the lactic acid concentration times the hydroxide concentration over the lactate ion concentration. In terms of X, that's 0.0307 plus X times X over 0.0682 minus X. And solving for X, in this case, gives us 1.6 times 10 to the minus 10th molar. Now note, this X, first of all, it's a very small number, and second, it's what's added to the 0.0307 molar to give us our hydroxide concentration at the end. Now, that's a very, very tiny amount. It's negligible when we add it in. It's not going to show up at all to our significant figures. So we have 0.0307 molar hydroxide. And as before, we're interested in the pH. So we take the negative log of the hydroxide concentration to get the pOH, subtract that from the 14 to get the pH, and that gives us 12.49. So very high pH when we're past the equivalence point, which is what we'd expect with a strong base. And that does it for this weak acid strong base titration calculation screencast.